Okay, we're going to look at example C. Again, example C is an index inequality, but you'll notice this time there are two inequality signs as opposed to just one, and this is called a double inequality. What we want to do is obviously solve it, and by solving it we're going to find the value of x which makes the double inequality hold. In other words, 1/9 will be smaller than the middle bit and the middle bit will be less than or equal to 5. Now in order to solve this we have to break it up into two separate inequalities. And the way to do this is first of all to take your hand and basically cover up the inequality sign that's furthest to the right and everything after it. So there's the first inequality you're going to solve. What we do now, again, is we take our hand and we cover up now the inequality sign that's furthest to the left and everything before it, and there's the second inequality that you're going to solve. Now, we just solve the two separate inequalities separately. So the first one here, again, we're going to take natural log of both sides. We're now going to make the power the coefficient of the log. Again, I don't like the fact the term that contains x is negative, so I'm going to shift it to the other side to make it positive. And then shift the natural log of 1/9 over to the other side. Okay, we're going to divide both sides by the coefficient of x, which is natural log of 2, and that's okay. If we're dividing by natural log of 2, so we're dividing by a positive, so the inequality sign does not reverse direction. So we're going to end up with x is less than minus natural log of 1/9 all over natural log of 2. Now, we're going to go to your calculator then and get a rough idea of what that is. Now, just before we do that, believe it or not, this answer is going to be positive. Now, there might be some of you thinking, but hold on, you're taking the natural log of 1/9. Is that not negative? Yeah, natural log of 1/9 is negative because that's between 0 and 1, so you're going to get a negative. But then it's being multiplied by a negative here, so the top line is going to be positive. You're going to be dividing by a positive, so we are expecting this to be a positive answer. So we're going to have x is less than, and then go to our calculator. And that's going to give us 3.1699. Okay, and then what we're going to do is we're going to solve the second separate inequality. Same idea, going to take natural log of both sides. Again, make the power the coefficient of the log. Again, I don't like the fact that this term here containing x is negative, so I'm going to shift it the other side, and then I'm going to shift natural log of 5 over. Now I'm going to divide both sides by natural log of 2, and remember we're dividing by natural log of 2, which is positive, so that will not reverse the direction of the inequality sign. And then again, this time before I type this into calculator, I'm expecting this answer to be negative, because natural log of 5 will be positive, but we're multiplying it by a negative, and then we're dividing by a positive. So it is going to be a negative. So that's going to give us negative 2.321. Now, when we solve an inequality, we don't like it when x finishes on the right hand side. We always want x to be written down on the left, but even if you move x over, it's going to be negative. So you can't move x over and change its sign. So instead, we have to use common sense. Minus 2.321 is less than or equal to x. So that's the same as saying, well then x must be bigger than or equal to minus 2.321. Now, at this stage, what we do is we're going to illustrate each solution on a number line. Now, we didn't have to do that in the previous examples because there only was one answer. Okay, there only was one inequality that we were solving. We're now solving two separate inequalities. So what we're going to do is we're going to show their solutions on the same number line. Okay, so minus 2.321 and then 3.1699. Now, x takes values less than 3.1699, so I'm going to put an open circle above that value because that means x can't actually take that value, and then we're going to draw an arrow to the left because x takes values less than that. Now, x takes values bigger than or equal to minus 2.321, so x can take this value here, so I'm going to put a closed circle above it, and then the arrow will be going to the right because x can take values bigger than it as well. Now, the reason we show both separate solutions on the same number line is because we want to identify the overall solution that satisfies both inequalities, and that is given by the overlap region. So the overlap region is where the two arrows cross over each other. So they cross over each other between 3.1699 and minus 2.321. So that is our overlap region. The overall solution for the double inequality is the solution that describes the overlap region. So how do we describe it? Well, the first thing I'm going to do is write down the end values of it. So we've got minus 2.32, and then the other end of that overlap region is 3.17. I've just rounded those to 3SF. And x can take any value between those, so I'm going to put x in the middle. And then we need to decide what inequality signs go between minus 2.32 and x, and between x and 3.17. So go back to the solution here. We're told that x is bigger than or equal to minus 2.321. So if x is bigger than or equal to minus 2.321, then minus 2.321 must be less than or equal to x. If x is bigger than or equal to it, then it must be less than or equal to x. And then if we look at the solution for the other separate inequality, x is less than 3.1699. So the relationship between x and 3.17 is x is just less than it. And what we have here is our final answer. That is the range of values of x which satisfy the original double inequality. So in other words, if you chuck in any value of x between minus 2.32 and 3.17, but not including 3.17, you chuck that into here, then this inequality will hold. If you chuck any other value of x in, then this inequality will not hold. So that is our final answer.